Have you ever seen log base 2 of 8 equals 3 and wondered how that even works? Or wondered why you're not allowed to put a negative number inside a logarithm? Today we're going to demystify logarithms by tracing them back to their roots, the exponential function. By the end of this video, you'll see logs are no more mysterious than basic algebra. Let's start with the function f of x equals 2 to the x as an example, and let's review some characteristics. Keep in mind that all these characteristics will be true for any base. As with any function, we start with the domain, the set of real numbers, and the range, the set of positive real numbers. Note that we're working with a function where the codomain and the range coincide. As far as characteristics go, notice that the graph has a y-intercept at 0, 1 and a horizontal asymptote at y equals 0. Most importantly for our purposes though, the function passes the horizontal line test. This means f is a 1-to-1 function, and as such it has an inverse function. Let's call this mysterious function the inverse of f, the standard notation for inverse. But here, be careful with the notation. Do not confuse the inverse of a function with its reciprocal. The -1 does not represent a power in this case. By the definition, the inverse must take us back from where we started. This means that domain and range are flipped with respect to those of f. This gives us the equations representing the connection between f and the inverse of f. The inverse of f of x equals x, and f of inverse of f of x equals x for all x in the corresponding domain. Replacing f, we get that, by definition, the inverse of f is the unique function that verifies the equations f inverse of 2 to the x equals x and 2 to the inverse of f of x equals x for all x in the respective domains. We know more than that though. For instance, we know how its graph must look like. To sketch the inverse of f, we first draw the line y equals x and then use it as an axis of reflection. We pick a point in the graph of f and draw a perpendicular line with respect to y equals x until we have a point equidistant to the line on the other side. To create the graph of inverse of f, we just see the shape created by moving the point. This process shows that inverse of f has a vertical asymptote at x equals 0 from the horizontal asymptote of f and an x-intercept of 1 from the y-intercept of f. For being such a mysterious function, we seem to know quite a bit. Domain, range, graph, property is inverse, x-intercept, and asymptote. It is for this reason that it makes sense to give it a name, logarithm, and special notation. The 2 is called the base of the logarithm since it was derived from f of x equals 2 to the x. Its defining properties are exactly what we derived. Log base 2 of 2 to the x equals x, and 2 to the log base 2 of x equals x. But don't let the notation get to you. There is nothing mysterious here. The logarithm is defined as the inverse function of the exponential. This is what it must do. This already solves one of the questions we posed. Why is log base 2 of 8 equals 3? We only need to realize that 8 equals to 2 cubed and then use the definition. This idea works for any acceptable base. If f of x equals a to the x, then its inverse is log base a of x. But what is an acceptable base for a logarithm though? As we've done so far, the answer comes from the base of the exponential function. They are easy to overlook, but constraints are part of definitions. In the case of the exponential function, we have that the base must be a positive real number different than 1. So negative bases would give undefined values for exponents like 1/2, while 1 makes a constant function, not quite as interesting. What about the graph? How does the graph look like when we change its base? Different bases change the shape slightly, but the inverse relationship still stays the same. Note that for a less than 1, the graph switches sides, but all the properties we mentioned aren't modified. Same domain, range, asymptotes, and etc. So in summary, there's nothing to be afraid with logs. They do what they must as inverses of exponentials. This philosophy applies to more advanced properties like log rules, which we didn't mention here, but which we might make a video on in the future, so be sure to leave a comment. So next time you see one, overcome that initial hit notation like this gives, and remember logs are a rather well-behaved bunch. This video is brought to you by Lighthouse Global, your personal online tutoring for IB, college applications, and school subjects.